Another test for convergence is called the p-series test. So it's when the terms are made up of a pattern like 1 over n to the p. Okay, so the base changes, so like 1, 2, 3, but the power stays the same. Okay, so what needs to happen is that the p needs to be a positive value, and then we're going to dive a little bit further into a special series, p series, called the harmonic series, and it's when p is equal to 1. So like 1 over n to the first power. Okay, so the sum from n equals 1 to infinity of 1 over n to the first power. So we're going to look at that now. Actually, what we know about the p series is that um, the series converges if the power is greater than 1, it converges. If the power is between 0 and um, and 1 is greater than 0 and less than or equal to 1, then the series diverges. And we just need to remember that p has to be greater than or equal to 0 to be considered a p series. Okay. All right, so we're going to look at the harmonic series, and I know that the harmonic series diverges, and this is why. So the harmonic series is just 1 over 1, 1 over 2, 1 over 3, 1 over 4, so on and so forth. I wrote it out for you. Okay, so if I add up the terms of the p series, I'm hoping that it goes to a finite number. But what I see is that 1 is equal to 1, okay? Then I'm adding 1 plus 2 plus 3 plus 4, which when I add that, that is a number greater than 1. So now I'm already adding 1 plus 1, that's 2. 1 plus 1/5 plus 1/6, all the way to 1/12, that's a number greater than 1. So that's another value I'm adding. So the sum so far is greater than 3. Then 1/13 to 1 over 31 34th is a number greater than 1. Another value I'm adding. Okay, this just continues. I have to add more and more and more terms to get a value greater than 1, but still I see that the sum is not going to be finite. So this just continues. So the series will diverge because we continually add more and more value as we add terms. So the harmonic series diverges, but we're going to say it diverges very slowly. Like we're not adding a lot, but it is definitely not going to a value. It's getting larger and larger. Okay, so the harmonic series again is the sum from n equals 1 to infinity of 1 over n. Okay, all right, let's do some more examples. So we're going to use the p-series test to determine convergence or divergence, I guess. Here we go. What we need to remember is that if p is greater than 1, the series converges. And if p is between 0 and less than or equal to 1, the series diverges. Okay? So looking at the summation, I'm like 1 over n. The 2 is the p-value, so p is equal to 2, which is greater than 1. So the series converges by p-series test. And you do have to identify the condition that it converges. So p is greater than 1. Okay. The second one I can rewrite as the sum from n equals 1 to infinity of 1 over n to the 1/2 power. So I can see that my p is equal to 1/2, which means that p is between 0 and 1. So 1/2 is between 0 and 1. So the series diverges by p-series test. It's not the denominator isn't changing fast enough, basically. It's not growing fast enough for us to diverge. Okay, so 1 over n, we know this one. This is the harmonic series. Okay, so we know that p is equal to 1, which is 0 is less than p, which is less than or equal to 1. So the p-series diverges according to p-series test, or because it's the harmonic series. It's so common that we can even say because it's the harmonic series. Okay, this one we're going to write the summation. So I need the sum from n equals 1. Well, I think we're going to use 1. I'm going to make this my a sub 1, a sub 2, a sub 3, a sub 4. Definitely seems like I should label it this way because there's like a lot of 2's in the second term and a lot of 3's in the third term. So what I noticed is that a sub n is equal to the 1 stays constant, the n value changes on the outside, so n gives me the value on the outside times the square root of n. Okay, I think I'm going to rewrite this as 1 over n to the first power times n to the 1/2 power. I'm going to add my exponents to give me n to the 3/2. So I get 1 over n to the 3/2. So the sum from n equals 1 to infinity of 1 over n to the 3/2, where p is equal to 3 over 2, which is greater than 1. So the series converges by p-series test. So the denominator is growing fast enough that the series is going to add to a finite number. Okay, last one. I am going to do this work on the side. I have n cubed times the cube root of n to the negative 11. So n cubed times n, using rational exponents, negative 11 over 3. And then since I'm multiplying the bases, I'm going to add the exponents. So I'm going to change the 3 to 9 over 3, giving me 9 to the negative 2 over 3. So this is equal to the sum from n is equal to 1 to infinity of n to the negative 2/3, or I can write that as 1 over n to the 2/3. So I see that p is equal to 2/3, which is less than or equal to 1, but greater than 0. So the series diverges by p-series test.